Welcome to the GlobalFoundries FD-SOI Technology webinar. My name is Sean O'Kane from ChipEstimate.com. Today, we're pleased to introduce our speaker, Jamie Schaefer, PhD, Leading Edge Product Line Manager in the Product Management Group at GlobalFoundries. Dr. Schaefer leads the product management team focused on delivering solutions for emerging technology nodes. Prior to joining GlobalFoundries, Jamie was a research scientist at Freescale Semiconductor, where he researched new materials, integrations, and processes for future CMOS transistors, and was a key contributor to the development of the high-K metal gate integration. He has authored or co-authored more than 30 publications, including a Springer book chapter, and is the proud recipient of the Freescale Distinguished Innovator Award, given to employees who have over 10 issued patents. Dr. Schaefer received his PhD degree in materials science and engineering from the University of Texas at Austin. Please welcome Dr. Jamie Schaefer.
Thank you. Thanks for that introduction. And thanks for hosting the webinar today, and thanks for attending the webinar today. My name is Jamie Schaefer. I'm with GlobalFoundries, and I'm the Leading Edge Product Line Manager. And the talk I'm going to give today is Extending Moore's Law with FD-SOI Technology. For the agenda, I will start off with a brief FD-SOI technology overview, where we'll compare the benefits of FD-SOI compared to bulk and FinFET technologies. I will then talk a little bit about the power, the performance, the area, and specifically the cost advantages that you can get from an FD-SOI-based technology. Next, I'll talk about some of the unique features of FD-SOI, actually one of the key differentiating features of FD-SOI compared to bulk and FinFET technologies, and that's the ability to do transistor control with body biasing to get the optimum trade-off between active and standby power for your applications. And then finally, I'll wrap up with talking about the applications that are ideal for FD-SOI and a few use cases and examples of how FD-SOI will benefit those applications. For many generations, the semiconductor industry has been driven by the ability to reduce the cost per transistor. This has been driven by advances in process technologies that have resulted in ever smaller feature geometries on the chip, resulting in more transistors per unit area. And this is ultimately then passed on as an increase in functionality to the consumer for their applications. Lately, starting with the 28 nanometer node and beyond, we're seeing an increase for the first time in the cost per transistor. This is driven by the fact that the ever-shrinking geometries are requiring additional patterning steps, sometimes double, and on some of the latest nodes, even triple patterning steps to pattern a single layer on the transistor, single layer in the semiconductor. At the same time, many of the advanced transistor architectures and devices are requiring new materials and new processes. Both of these factors have the impact of driving up the manufacturing cost of the latest, most advanced transistor nodes. The effect that this is having is many applications are being slowed in terms of their migration from the 40 nanometer node or from the 28 nanometer node into the 20 or the FinFET node technologies. And this is delaying the adoption rate of FinFET for many cost-sensitive applications that just can't make that migration from 28 into FinFET. The solution we'll talk about today is FD-SOI. You'll see some of the benefits of FD-SOI and how FD-SOI can continue to lower the cost per transistor for some of these advanced nodes, while also providing differentiated power solutions for these emerging applications in these low-cost markets such as IoT. To understand FD-SOI and how it will play an important role for these markets, we first need to understand the benefits and then the limitations of FinFET and bulk CMOS technologies. FinFET is the right technology for applications that demand the highest performance and also require the best digital area scaling. Many applications such as high-performance computing, server applications, and also applications such as premium smartphones, which require the highest volume manufacturing. FinFET is the right solution for many of those applications. FinFET, however, is a more complex manufacturing process. It requires many double patterning steps, and this is driving up the cost per transistor. FinFET also has new design flows that are complex and result in increasing design NRE. We can contrast this with the incumbent solution today, which is a planar CMOS or a bulk CMOS technology. These have very mature design flows. They leverage mature manufacturing processes, which can result in lower costs. But the overall roadmap for FD-SOI is very limited after the 28 nanometer node, and improvements upon that are incremental. Bulk CMOS tends to suffer from increased leakage and variation as you scale these transistors beyond the 28 nanometer node. And this means that many applications that are cost sensitive and can't migrate to FinFET are then stuck with a solution that doesn't have any sort of differentiated power or performance. FD-SOI, on the other hand, is a cost-effective alternative to FinFET and bulk technologies for these smaller die applications. Here's an example of FD-SOI. You can see it has a fully depleted channel. The fully depleted channel can result in lower leakage through better electrostatic control of that device. It also has an ultra-thin buried oxide layer, so that fully depleted channel is similar to a FinFET in that it's, except for it lays planar instead of in a vertical architecture. That fully depleted channel is then separated from the bulk of the wafer by an ultra-thin buried oxide layer. This effectively eliminates a vast majority of the junction capacitance in bulk technologies, allowing for power reductions. And the fully depleted channel has no doping from extension and well implants, which results in a low improvement in mismatch and variation compared to bulk technologies. FD-SOI is a planar process, so it's very similar to bulk in construction, and this also allows it to leverage the design flow and many of the EDA tools that are used for bulk technologies. FD-SOI can have up to 20% lower die cost than FinFET. This is driven by a couple things. For one, FD-SOI is inherently a lower process complexity technology than FinFET. It has fewer masking steps than 28 nanometer bulk technologies. It also has significantly fewer masking steps than a FinFET technology. FD-SOI is also scalable beyond 28 nanometer. This can also reduce the cost per die relative to 28 nanometer solutions. FD-SOI also has a 50% lower mask cost than FinFET. This is driven first by the reduction in the overall mask count, but also to the fact that it doesn't drive such a high reticle grade, which is one of the factors that drives up the mask cost on FinFET technologies. FD-SOI can be integrated with RF and analog, as well as embedded NVM to reduce the overall system cost and power for differentiated customer solutions. FD-SOI, and we'll talk more about this, can be architected for transistor body biasing. This provides some very unique capability to minimize active and standby or leakage power. Forward body bias can be used to access ultra-low voltage operation. You'll see example of down to 0.5 volts, and ultra-low leakage operation with the reverse body bias capability. Okay, so we've looked at some of the features of FD-SOI. Let's talk a little bit about some actual transistors. So this is a TEM of some of GlobalFoundries FD-SOI transistors. What you can see in these transistors is it's a very simple transistor architecture. There's a gate-first integration. There's dual raised source drains on both the NMOS and the PMOS regions. This provides a nice landing area for the contacts. There is the fully depleted channel region underneath that gate, and that is then separated from the body by an insulating oxide layer, which is responsible for a lot of the capacitance reduction and power reduction that you get in FD-SOI. That oxide layer separates then the bulk, or what is referred to as the backgate of the FD-SOI transistor. Now, the backgate can have a potential applied to it, which can dynamically control the threshold voltage of the NMOS and the PMOS transistors. So we'll talk more about the ability to do the body bias in a couple slides. Okay. So next I want to talk about, after talking about the features of FD-SOI, I want to talk a little bit about the power, the performance, and the area advantages that you get with FD-SOI technology. FD-SOI can be architected to provide differentiated cost and performance compared to the incumbent bulk and FD-SOI solutions today. Typically, for many nodes, technologies have moved up and to the left on this chart. But with recent nodes and the increase in manufacturing costs that's required, there's actually an increase in the normalized die cost for some of these advanced node technologies. FD-SOI, through the fact that it is lower process complexity and fewer masks than 28 nanometer, as well as through the fact that it can be scaled beyond 28 nanometer, can be produced with a cost per die that is comparable to the lowest cost 28 nanometer low power technologies or the 28 nanometer polysilicon-like technologies. At the same time, FD-SOI has a wide array of transistor boosters that can be applied to it to provide performance that excels or is in excess of the best 28 nanometer solutions, better than 20 nanometer solutions on the market today, and can even compete with FinFET-like solutions in terms of active power. So next we're going to look at how this power, performance, and cost advantages benefit the target markets for FD-SOI. So currently, the highest performance applications in 28 nanometer have already made the decision to migrate into the 20 and the 14 nanometer FinFET node. And that is the right solution for these applications. These tend to be large die, say 250 millimeter square die, with the highest performance requirements, and they require the most digital area scaling. And so FinFET is the right solution for these applications. However, many of the low power solutions, low power technologies in 28 nanometer that tend to be a little bit more cost sensitive, are having difficulty migrating into the FinFET technology node, but they still require the power and the performance benefits that you can get out of an FD-SOI based technology. This is where FD-SOI provides the right solution, and FD-SOI will win the low cost applications that still have the demanding power requirements. FD-SOI is ideal for applications in the low to mid-tier mobility market, for wearable applications, applications in the consumer and the automotive and industrial segments, as well as IoT and Wi-Fi and RF applications. In particular, applications that tend to have a higher fraction of analog content and don't require the ultimate in digital logic scaling, don't require FinFET, and are even more cost challenged to migrate into the FinFET node. FD-SOI provides these applications a great low-cost alternative with unique options for power and performance optimization. So next I want to talk a little bit about one of the unique features of FD-SOI, and that's the ability to do transistor control with body biasing to optimize for power and performance trade-offs. This is just an example of an FD-SOI transistor to show how it can be architected for effective body biasing. This provides the greatest power efficiency and design flexibility. The body biasing is applied similar to a bulk technology through well taps at the edge of the arrays. NMOS devices and PMOS devices are biased in a way that can either raise or lower the threshold voltages of these devices dynamically. Through the use of forward body bias, this is lowering the VTs of a block of NMOS and PMOS devices. It can enable low voltage operation down to 0.5 volts without speed loss. It can also be used to boost performance for periods of time if needed as well. Reverse body bias, this is the ability to, this is raising the VT of a block of logic devices. This is ideal for logic devices that require lower standby leakage. And reverse body bias, when the devices are optimized for it, can enable low leakage down to 1 picoamp per micron. So dynamic body biasing, the ability to do this dynamically, enables active trade-off of performance and power. And body biasing can also be used similar to adaptive voltage scaling to reduce the variability across the die and or die to die as well. Okay, so next I want to give an example of how body biasing provides the maximum flexibility between leakage power and frequency. To apply reverse body bias, you essentially apply a negative voltage to the NMOS devices and positive voltage to the PMOS devices. This has the effect of raising the VT of that block of logic devices to put it into a minimum leakage or a standby mode when those devices are not active. Similarly, devices can be architected for forward body bias. In this case, a positive voltage is applied to the NMOS devices and negative voltage applied to the PMOS devices to lower the threshold voltage of all these devices. And this can be used to increase the frequency or boost the frequency to get the maximum performance for a period of time. Now, a lot of the real power of FD-SOI comes from the ability to combine DVFS, or dynamic voltage frequency scaling, with dynamic body bias to get the best performance between active power and leakage power. So I'll walk through a simple example here, and then I'll show some actual silicon-based model data. This slide shows what you can do essentially by raising and lowering the VDD of the core device. So by raising the VDD of the device by 100 millivolts, you can boost the performance, but it comes at the penalty of a relatively large active power. Similarly, the VDD of a device can be reduced, lowering the performance, but it comes with relatively minor gain. It reduces the active power, but comes with relatively minor gains in the reduction of the leakage power for standby modes. So if we compare this with what you get with forward and reverse body bias, you can see that you can apply a forward body bias to reduce the VT of those devices. This results in the same amount of frequency gain that you would get by increasing the VDD, but you're now doing it more efficiently in terms of active power. So your active power consumption is less for the same frequency point. If you look at the reverse body bias, you can also reduce the performance or reduce the frequency by raising the VT of those devices. But you're getting a much bigger gain or a much bigger reduction in the leakage power by applying the reverse body bias than you are by just simply reducing the VDD. Now, when optimizing the libraries, PVT and body bias points can be selected to combine and get the optimum trade-off between active and leakage power. This shows some of the more interesting points that can be achieved by doing this, by applying by overdriving the devices with VDD and applying forward body bias, the best performance can be achieved. By going to lowest possible VDD and applying forward body bias, this allows for low active power without sacrificing performance. So it's the best performance per watt operation condition. And similarly, the active power can be reduced by lowering the VDD, and the leakage power can be reduced simultaneously with applying the forward or reverse body bias condition and raising the VT of the devices. This gives the designer the ability to access a lowest total power state for the devices. Okay. So let's look at some actual model-based silicon data to see some of these benefits. What's shown here is a 28 nanometer high-K metal gate benchmark technology. It's a high performance offering, so it's not a low power or it's not a polysilicon offering. It's a 28 nanometer high-K metal gate offering. And I'm showing the reduction in power you get at the same ISO frequency, as well as the improvement in frequency you get at ISO total power with a advanced node FD-SOI technology offering. You can see here that you get 50% lower total power with FD-SOI compared to a high-performance 28 nanometer offering, at the same frequency. This is essentially 200 millivolts lower VDD. You're getting the same frequency as compared to a 28 high K offering. Similarly, you can go to higher frequency at the same total power and get about a 41% frequency boost. The other curve I'm showing here is the forward body bias condition for FD-SOI. With that, you can essentially approach FinFET level performance. And you can see from this curve that if you extrapolate here, you can get essentially the same performance at about 350 millivolts lower VDD, or about a quarter of the power consumption from a 28 high K metal gate offering. This is done by lowering both the dynamic power at the same frequency, by lowering the VT of those devices and lowering the VDD simultaneously to maintain lower active power. FD-SOI also offers multiple types of transistors to optimize for both leakage and performance. FD-SOI has low leakage the lowest VT transistors, so these tend to be the highest leakage, and they're optimized for forward body bias. They have the highest performance, and these are the transistors that you would apply forward body bias to get the ultra-low voltage operation conditions. There's also a set of transistors with mid-range VT. These are the right balance of low leakage and high performance and are optimized for reverse body bias. So when not in use, they can be put into a low standby leakage state to minimize the leakage consumption. And ultra-low leakage devices, so devices can be optimized strictly for leakage. These are coupled with the ability to reverse body bias to achieve the absolute lowest leakage floor of about 1 picoamp per micron leakage. So there are multiple transistor options to optimize for both leakage and performance. And the range of leakage that is spanned by these devices is quite large compared to many of the bulk and FinFET offerings today. Okay. So let's take a quick look at an example of how this can be applied into a system on chip. So both the forward body bias, the body bias features, as well as these different VT points. So this is an example of a typical, say, IoT system where you would have a watchdog processor that is just looking for some sort of input or trigger. These devices would be in a low leakage state. They would be constantly on, but you would want to minimize the leakage and the power consumption on these states. So you would use the reverse body bias devices for these. That device, once it sees the trigger or it detects a motion, it would then activate another block of devices. These would be optimized with forward body bias devices and optimized to have the absolute lowest dynamic or active power. In this case, in this example, it's waking up an image processor, which would then zoom in and analyze. For the case of an image processor, it's important to have the low dynamic power to minimize the thermal budget for that image signal processor, as well as the ability to minimize battery or maximize battery life and minimize power consumption when operating a video. And finally, FD-SOI has the ability for integrated RF. So once that image is analyzed, and it can wake up the integrated RF and transmit the message to the edge node server, or and transmit that message. Okay. So FD-SOI delivers the low static and dynamic power to optimize for SoC applications. It has the RF integration to reduce the overall bill of materials, and the forward and reverse body bias are ideal to optimize the SoC for specific use cases or use modes. So how is all this applied then in the design flow? FD-SOI actually leverages bulk design flows. There are a few modifications that are required in order to do this. So the first step is that the library characterization has to be done with the body bias points in mind for the application. There is some planning that is required because the forward body bias and the reverse body bias blocks and the wells are different. So this needs to be done a priori. by the designer during the RTL synthesis stage. There are some specific FD-SOI specific placement steps that are done at the next step. And then the tap cell conditions leverage existing bulk UPF or IEEE 1801 low power flows for the tap cell connections. This is not any different than how a typical bulk flow with body bias applied would be done. And then the body bias mesh planning is done at that stage. The leakage recovery with VT swapping and L-gate optimization is done in a similar fashion. There are forward body bias and reverse body bias blocks that would be optimized for power and performance. And then during the sign-off stage, there's some added corners for the body bias variable, so the PVT corners with the body bias variables included. Okay, so next I want to talk a little bit about the applications for which FD-SOI is ideal. FD-SOI can provide differentiated value for the target applications. These are a list of applications where FD-SOI can play a very important role. So in consumer applications, there are demanding Energy Star requirements that come up near the end of 2016. FD-SOI can exceed those requirements in terms of power reduction and also enable the smaller form factors that are required for many of those applications. For wearable applications, wearables have to be optimized for specific standby and active power use cases. FD-SOI can accomplish this and produce longer battery life for a 205 milliamp hour battery. It also has the RF integration to reduce the overall system cost for wearable devices. In the IoT and industrial space, FD-SOI can meet the requirements of high-density image processing and video decode. It has the integrated RF and embedded non-volatile memory, and has the power at 0.6 volts for active power reduction to improve the battery, to enable all this with battery-operated battery-operated devices or battery-operated products. In the low to mid-tier mobility market, FD-SOI can meet the 60 frame per second display requirements for the next generation of that market, the 1080p video requirements, and the Cat6 LTE wireless needs without going to the FinFET costs. So this is a market that really leverages the performance that can be achieved with FD-SOI. Also, with that performance, you can minimize the overall cost by enabling a dual-core solution rather than a quad-core solution, a more costly quad-core solution. In the automotive and infotainment space, the lower junction temperature at a 125C ambient, as well as the better soft error rate, which is inherent in the SOI architecture, can provide value for FD-SOI in these applications. And finally, the most advanced nodes of Wi-Fi and RF right now are at 28 nanometer. These are very cost-challenged to migrate into FinFET, since the analog area scaling does not scale very well into FinFET, and FD-SOI provides a good solution to achieve higher data rates at lower power for these applications, as well as through the use of the body bias, some unique features or capability for the analog chip designer to improve circuit topology. Okay, so let's take a example. This is a case study for a smartwatch. So this is a next generation smartwatch device where you would have about a CPU frequency of about 1.5 gigahertz. You'd want to be able to operate it down to 0.6 volts. And you need an integration path with Bluetooth, LE, Wi-Fi, and power management ICs. If we start with a 40 nanometer wearable device today, and we look at an example of the battery life improvement that you can get with FD-SOI compared to 40 nanometer or compared to FinFET, you can see that the battery life can increase due to the power reduction at ISO frequency, which is about a third, from 4.5 days up into almost 14 days for the FD-SOI solution. So it's about a 3x improvement in that battery life. If we look at some of the other features of FD-SOI, and you start applying the forward body bias feature for FD-SOI, you can now have a power that's only about a fifth of what you get from a 40 nanometer application. This can extend that battery life from 4.5 days up to about 19 days. So about a 4.4x improvement in that battery life. And then if that battery life isn't required, you can also improve the functionality of the device by adding in the Bluetooth LE and the Bluetooth LE plus the Wi-Fi capability. This takes away some of the battery life, but you still have up to 14 to 18 days of battery life, but you've improved the functionality by adding in the Bluetooth LE and the Wi-Fi to reduce the overall system cost and provide more functionality to the end user. So next I want to talk a little bit about how FD-SOI enables IoT growth. So a typical IoT edge node has the microcontroller unit, the power management, and the connectivity integrated, and the sensing de-integrated. FD-SOI provides a good solution for the demanding power requirements for IoT chipsets. It has the ultra-low voltage operation with forward body bias in active power modes when low active power is required, and it has the ultra-low leakage with reverse body bias when the best in standby power is required. FD-SOI also has the low cost to meet the needs of the IoT growth and the IoT market. So it's a planar process similar to bulk. As we mentioned, 20% lower die cost and the 50% lower mass cost than FinFET, and also the ability to integrate the RF and the MVM to lower the overall bill of materials and the overall system cost. And FD-SOI then provides the ability to integrate the RF, the embedded NVM, and the power management, the integrated analog into the system to meet the needs of the IoT growth. Okay, I wanted to talk a little bit about the growing industry support for FD-SOI. So right now there are multiple foundries that are supporting FD-SOI. GlobalFoundries, ST, and IBM have all contributed to some of the foundational work in the FD-SOI development. Samsung is developing an FD-SOI foundry offering of their own as well. There have been multiple companies, an increasingly large number of companies, who are making public announcements about adopting FD-SOI. A few of those are listed here. And then GlobalFoundries is working with our ecosystem partners to build out that ecosystem for both design services and design enablement. So there's EDA providers. There's a wide array of IP and design services companies, including Invecus, who's GlobalFoundries' dedicated IP provider. And then there's multiple substrate suppliers who are ensuring the substrate capacity for high-volume manufacturing of FD-SOI in the industry. There's also numerous industry groups who have been dedicated to the success of FD-SOI to continue to help build out and grow the industry support and the industry ecosystem. So in summary, FD-SOI is a cost-effective alternative to FinFET. It is ideal for applications like IoT, consumer, and low-end mobility markets. It can integrate the logic, the RF, and the embedded NVM on the same die to reduce the power and the overall system cost. We talked a little bit about the optional body biasing feature. This is for the flexible trade-off of performance versus power and to provide the designer the best active and standby power reductions. FD-SOI also leverages bulk digital design flows and existing EDA tools in the industry. And there is very strong industry support for FD-SOI, and it is scalable down to 10 nanometer. This ensures that FD-SOI has a very bright future. Thank you for your time today.
Excellent. Thank you so much for the information, Jamie. In the little bit of time we have left, we have just a few questions from the audience that we hope you can answer. So question number one, specific to GlobalFoundries, what have been some of the challenges in the development of FD-SOI technology?
I think the biggest challenge has been FD-SOI is ideal for low-cost applications, and so it's finding the right positioning for the market acceptance of FD-SOI and architecting it for both a low-cost solution as well as a solution that can provide extended roadmap for differentiated power and performance for the applications in new emerging markets such as IoT.
Okay. And last question, can you describe the ecosystem surrounding FD-SOI? For example, what what type of IP solutions will be available?
Yeah, so GlobalFoundries is committed to working with our ecosystem partners. We have a dedicated IP provider through Invecus, who is developing IP for our leading edge applications and leading edge technologies.
Perfect. Thank you so much. And thank you for joining us today to learn more about GlobalFoundries FD-SOI technology and our webinar today. Thank you, Jamie.
Thank you.